Prep to be pro.
All right, welcome everyone to the SRE Meetup. This is the 5th edition we do, right, Kirill? Yeah, 5th. Good. So my talk will be about circuit breakers, but I'm not gonna give a lesson about circuit breakers. Okay, this is our experience on how did we decide to implement circuit breakers in the company, and what challenges did we face. Let me introduce myself. I'm Marcos. I've been around at Preply almost for 2 years. It's been an exciting journey. Preply has been existing since 12 years ago. So you can expect that at Preply we have legacy, of course, but we are adding features. I will explain further about this legacy and how it has affected ourselves in our decisions and so on. But overall, I will try to answer main question, explaining why do we need these circuit breakers at all in order to safeguard the systems. Also, what unexpected things did we face. I will share several incidents through the talk. I believe there are 3 of them, one of them really big. Well, there are a couple of them that are severity ones, so, but the last one has a dedicated point because it's the most funny. And at the end, I will share a bit of retrospective on what's the current state, what that have we achieved, and what are the future plans around circuit breakers. Okay. So answering to the question, let me first put you in context on what's more or less the shape of the traffic at Preply. So you can expect that we have lessons, and normally the lessons start at each hour o'clock, right? So you can see that we have early spikes that go really out of the normal baseline of the traffic. So yeah, this picture is taken from this Monday. We are crossing 10K hits per second on the early spikes that normally are at 5, 6, 7 p.m. Barcelona time. And you can expect that most of our scalability problems happen at those times. So this is one of the biggest challenges we face at the company. We are using Django. So everything is programmed in Python, but using the Django framework. So let me explain a bit. So we have this monolith approach. What does it mean? We have monorepo, and we have several applications running inside this monolith. And it's, let's say, from a perspective of infrastructure, there's a single pod that will serve the different applications. And it's one pod that fits for all of them, right? So as I said, we use Django. So Django is the framework, and we serve the request using Unicorn. This is the web server. And Nginx is as well a web server, but in this case, in Kubernetes environment, it will act as a proxy. And the web will be rendered using Unicorn. Unicorn has a limited amount of workers that can be configured, of course, and you can also configure how many requests will it serve before restarting and so on. So one of our challenges is configuring this properly. Why? Because we have observed that whenever, this is the average hit rate, but for the Unicorn workers, this is not for a single pod, right? So when we exceed certain threshold, in this case, more or less is 300 hits per second, then we start seeing one funny effect that it's request queuing. Okay, does anyone know what's request queuing? Yeah, so request queuing is the problem that when the request enters the web server, how much time does it take to give the response, okay? So if several requests keep queuing, remember that we have limited amount of workers. So at the end, we don't have enough workers to serve this traffic, okay? And then problems start to arise. So we try to shape our auto-scaling based on schedule, so that whenever the hour is going to approach, we scale up our monolith pods. Why we do it in a schedule? Because our pods take more or less 2 minutes to be able to serve the traffic. So remember that it's a monolith. So we have to do it beforehand, like preparing for the traffic instead of being reactive on the CPU or the memory being consumed, okay? So this is more or less how we approach this issue. So what do you think can be the main issues of this request queuing? Here you are the spoiler. So we have third-party APIs where if a request comes, I need to check some data out of the cluster, then the answer comes back, then I reply to the user, right? So all this time accumulates. Also maybe payments, if we do it in a synchronous way. Also some tracking, whatever the use case is. Maybe we need to validate some new tutor, and this can provoke this this long time to serve the response. And of course, also the database connections. So when I request to the database, depending on which query, how is it optimized and so on, it can take long. Also Redis connections, Elasticsearch, and so on. And this delay can be provoked by anything, let's say. Okay, so let me jump in to the first issue that made us think about how to react to this kind of problems, okay? So this is a postmortem story, February 2024. We were happily working in our projects, and we had to stop everything because of this incident, and stop everything and think, how can we prevent this from happening again? Because it was completely unexpected. So in this case, developers did enable a new feature. So we have the feature switches, just one admin configuration that you can flip, and then the feature is on. But this configuration that needed to work was stored in Redis, and it was a huge configuration for whatever the reasons the developers had. What happened then? Each request that we were receiving needed to retrieve this configuration from Redis, which was huge, like 100 megabytes. For this multiplied per all the requests that we were receiving per second, provoked that after more or less 1 hour of the feature being on and working perfectly, AWS started to throttle us because they have some limits that we were not aware of. And Preply went down because Redis, in this case, was not responsive, and the pods started to crash loop and so on. So it was completely mind-blowing, right? So we stopped everything, we sat down, we wrote the postmortem, shared it, and what can we do to prevent this from happening again? So one of the action items was to implement circuit breakers to safeguard our system. So let me explain a bit on the surface. I will not really dive deep on what's a circuit breaker, okay? But this is like the device that you have at your house, maybe next to the entrance door to handle the electricity. So whenever something goes wrong, the circuit breaker will open the circuit, and then the electricity will stop passing through, okay? Then you can go there and put the lever up manually, and if everything is okay again, the electricity will arrive to your place, right? There are some devices that also can try to go up automatically. In computer science, the pattern, the design pattern explains that we will measure some metrics, and when we are on the threshold, we will ignore those common failures. But if we exceed the threshold, the circuit will open, all right? So then we can improve the system, and we can set some timeout. And after this timeout, the circuit can try to open a bit, leave some traffic on, and if everything works, we can open it for the 100% of the traffic, all right? One of our decisions here, when we wanted to implement it, was to make it really simple, because we wanted to have a POC, or let's say an MVP of this feature really quick. So we did ignore the half open state, and we directly moved from close to open, all right? And to store the state, we did use, in this case, Redis. The counters were on Redis. We were adding there the counters on latency and also on errors. And the state was, do you remember this feature switch that the developers wanted to turn on and off of that feature. So we use the same capability so that the circuit breakers would automatically open there, but we could have this admin panel to be able to close it manually. We didn't have any automation to close the circuit back again automatically. So for the starters, everything was manual. So yeah, the open circuit was automated, but the close was manual, all right? So programmatically, what we did was to give abstractions of what a circuit breaker should look like. So we would have the state. If you remember, this is on the database using these feature suites and so on. The half open state that will not be implemented. Also the counters, and we will be worried about the latency and the error rate, all right? Obviously, the latency is too long. It will also provoke timeout error, but it can be any kind of error that adds up to this metric. And latency threshold, even if the response is correct, if it's a normal latency threshold, we will consider that something's wrong and we prefer to open the circuit, all right? Any questions so far? Everyone's lost? All right. So how did we approach this in our example? I talked before about third-party APIs, okay? But let's rename this point to requests library. This is the HTTP library that we use to make the requests. Why I want to rename it? Because we also use it for internal requests. It's not only third-party APIs. We also use this for our APIs. I don't want to call it internal. I will explain later why. But yeah, our own APIs. So what did we do for this? We would patch this requests library, okay? We can, there's some way that I will not dive deep, but if you are curious later, we can talk about it. We did set a global timeout, allowing override. And if the circuit is open, we will start returning directly 530 responses, okay? The implementation is quite, let's say, intelligent. So if something is wrong with a certain domain, it will only open for that domain. We don't have the request library not working for all the requests, only for certain domains, okay? So if I'm requesting PayPal and PayPal doesn't work, just open it for PayPal. The rest will be working still, okay. Database connections. So PostgreSQL, this is the main database. If PostgreSQL is not working, even the circuit breakers could not work, so we decided to assume the risk, okay? This is, or let's name it, point of failure, that when the database is wrong, everything's wrong. So we have other things to fix. We don't have any capability right now to be able to switch the traffic to a secondary master or whatever, so we just assume the risk. About Redis, what we did was to set up fallbacks when possible, in the sense that we can return some dummy data, or we can fall back to the database and so on. So when the circuit is open, we can return empty set or error, or it depends on the use case, because we have several Redis clusters, okay? Elasticsearch, what we did was to prepare dummy results, okay? Users come to the page, search for tutors, filtering by language or by subject, by price, etc. When the circuit is open, it doesn't matter what they put, they will be served some set of results that we consider that majority of users look for that. And yeah, they will be maybe not happy, but at least we don't show a blank page, which is worse, okay? And at the end, I added here RabbitMQ. Why? Because we had some fallback capability, but it was limited. We worked into improving it, and we can use now Redis as a fallback based on the same metrics as the rest of the circuit breakers, latency and errors, okay? So Redis is able perfectly of handling queues, and we use it as fallback, and it works. All right. Last but not least, we want to be able to observe what's happening with the circuit breakers. So we added a bunch of metrics in all the states of the circuit so that we can track how many requests use the circuit when it's open, how many requests use it when it's closed, and we are able to see, sorry, because it's super small size, but we can differentiate with the name of the circuit. And we built this super good-looking dashboard that obviously at the beginning didn't look like this, but we kept working on it based on our needs. You see here, we are keeping requests under 300 per second, so this looks quite nice and so on. And this is like, let's say, a normal state of the dashboard. All right, but you know, right? Okay, yeah. Let me first explain this example. So here we can observe how the requests to app.drive.so were having increased request duration, okay, up to 5 seconds. Then timeout did raise as an error, and the circuit was open here. If you can see this small dent here, the circuit tried to close, but it reopened again. Why? Because we again had increased timeout, request duration, let's say. So it kept open until it was good again and everything went to normal. Okay, what comes with monitoring? Everyone knows, if you want monitors, what do you want to happen? That is something was wrong, we have alerts. So the unknown. With alerts, we had a lot of noise. Our team was woken up at any time because we had circuits that were critical, others we didn't care too much, but how to differentiate, right? We had configured dynamic alerting in Datadog, so we didn't specify which one wanted to alert, which one didn't, because we configured for everything, just that. At the beginning, we had some of the circuit breakers in dry run because we wanted to be sure that they worked as expected, having our metrics. And as mentioned at the beginning, we didn't automate anything. So whenever a circuit was open, it was expected from us to go there, close it, see if it didn't open again, and go back to sleep, okay? So what can you expect with these ingredients to happen when we have some circuits on dry run, others that are serious to act, and so on? Anyone? Chaos, yes. Human failure. We are humans. So what happened in this case? We had Elasticsearch. Do you remember that we served this dummy page with results that probably the user wasn't even looking for? So yeah, Friday afternoon, we went home. Oh yeah, this circuit breaker's noisy alert again. So on Monday, our surprise was that the customer support was trying to poke us. Hey, customers are complaining. The filters are not working. Results are always the same. And we were like, oh yeah, okay. We left the circuit open. So again, we had a postmortem because it was a severity 2. Not one, at least, not one, but it was a severity 2. So then we decided to implement this automatic closing of the circuit. At the beginning, we decided it to be 3 minutes. So circuit opens, we send a batch job that in 3 minutes will be processed, and the circuit will be closed again, sorry. Yeah, and still we didn't want to implement the half open because it was overcomplicated in the implementation. Good. But the story is not end yet. We had some period of calm since then, but then we have a really big severity 1 incident. Now, let me first start by the end, okay? What did we see that we had at the end? We had requests coming to preplay.com at some page, and we discovered, yes, that we were consuming our API using the public domain. So from our monolith, we were calling the edu API, but using preplay.com, using the requests library, all right? So request come, request go out, come again, and edu API at the same time, maybe in the same request or not, was requesting back to monolith. In this case, I don't know why, but it was configured properly using the FQDN that we have in Kubernetes. All right, that's fine. The request is kept inside the cluster, but I want just to mention here that we also had the liveness prof that depended on that. All right, so what happened? Sometimes when we scale up, the nodes are not ready when we expect it to be ready. All right. So we did not scale on time, so we started to see request queuing. All right, in our monolith. What happened with this? With monolith not being able to reply at time, our Edu API pods, liveness profs, started to fail. So it was a party of pods restarting continuously. The Edu API didn't work at all. Then, since it was not working, the request that monolith was making to Edu API started to time out. What happens when we have timeouts using the request library? The circuit opens. So here, yes, we can see that the circuit was open here. And I'm hiding this a bit because suddenly we received database alert that page status. This database alert was the one that made us aware that something weird was happening, okay? We went to see in the AWS RDS metrics. Let me go back a bit. You see here, request to preply.com. So it was quite mind-blowing, right? Good. So in this case, this dotted line here is marking what's the maximum amount of virtual CPUs you have in your RDS. So you can see here where we were trying to consume in that moment in time, okay, when the circuit was open. And we see the top consumer here, okay, this is users trying to auth, that's fine, that's expected, we usually have that. And the requests are answered quite quickly. But we had the switches being requested, yeah? Yes, sorry. This is on the 64 CPUs. Yes. Yeah, remember that we have a monolith, so we also have a pretty big database to serve all this pretty big traffic. So yeah, this is before we started optimizing our queries. We need to ensure that the reliability was guaranteed, so we had a super big database. Yes. Good. So going back to the topic, waffle switches were being accessed a lot. How much? We went to Datadog and we saw that more than 3 million requests were accessing at the same time to the database using the same query. All right. Also, we saw here monolith cache. What happened? Whenever we flip a switch, this cache that stores all the switch state is invalidated. So whenever we open the circuit, all the requests that arrive to our service need to reach the database to retrieve again all the switch values. All right? So remember this cliffhanger area? Can you expect what happened next? Let me show you. Can you figure out what's happening here? Exactly. Every 3 minutes, our circuit breaker was closing again the circuit and reopening again. With this close and reopen, all the cache was again invalidated, and so on and so on. And this trend that goes down bit by bit is because the traffic was lower bit by bit until it self-healed after more or less 20 minutes. All right, so let me show you the other spoiler. Yes, so we can see here that our circuit breaker was flapping. Here we had some manual interaction trying to pray and so on until it automatically went better. Okay, so in the next hour, we disabled completely the circuit breakers. We took a look at what happened, and we realized that on one part, we were breaking the cache and not repopulating it at a time. And also we figured out that any request that arrived when the circuit was closed, but the threshold was exceeded, did schedule not only once the circuit close, but many times. So we didn't have any safeguard to guarantee that the circuit was only closed again once. So yeah, this came out after we analyzed the issue. Good. So currently, in which stage are we? So we have refactored all this circular dependency with the Edu API. This is not there anymore. If you are curious about that, maybe we can give another talk about how we did it, because it's really interesting, but not in the context of this one. All right, some incidents are being not prevented, but mitigated thanks to the circuit breakers. Why I say it's not prevented? So circuit breakers are reactive. So when the issue starts, it will prevent it to become much worse, okay? So thanks to circuit breakers, we can have a severity 4 that it's automatically mitigated. Why? Because it was opening due to latency and error spikes. And the end result was that we only had 320 error 500s because we started serving the dummy page for some minutes. In this case, we increased the threshold from 3 to 5. And at the end, it automatically closed, and the users maybe saw some weirdness, but the systems didn't suffer of this request queuing because Elasticsearch was too slow to answer. Okay. Yeah, so current state thanks to this is that maybe we can start relaxing on call paging. We don't need to be called constantly because a circuit is open. And yeah, more for the team, we have to brainstorm if this solution of keeping the state using the waffle switches on the database is optimal, because we also could use Redis. It could also work, or maybe better, because we are not interfering with the caches and so on and so on. Also, we may want to introduce the half open capability, which could reduce even more the errors. We would not have this. In the case that the error persists, we wouldn't have, we would reduce maybe the scope of the errors to minimum, right? So it's always preferable. And the last point is this one, adoption within the company, because we have not yet found space and time to properly explain to the developers how to use this abstraction for circuit breakers for their own products, okay? We protected the infrastructure, but teams can use it to protect their own stuff. In example, payments team has a backup for Stripe, in this case, I believe they use. So maybe they can, but right now they need to manually switch to use the backup. But if they started to track errors with a circuit breaker, they could automatically fail over to the fallback, right? So yeah, we offer the tools, but we also need to promote them so that the company uses them. All right, so what I wanted also to remark is that all this process have been of how have we faced the failures, how have we worked on postmortems, how have we tried to push to the realization of our action items. So it's really important, because right now we feel that the system is much more, let's say, reliable in the case of failure, because we are able to mitigate it quite quickly. Okay, so I wanted also to present the rest of the team. We have pretty much distributed team. We have Anton and Oleksiy in Ukraine, Bogdan in UK, our engineering manager, Yuri is in Berlin, and Vitaly, Kirill, and Marcos, you know us because we are around. And maybe you want to join us and help us fighting this adventure or the next one. If you want to look for developer positions, they are also open. I have the filter on engineering, but there are many other open positions that maybe you can be interested in, or maybe share with some acquaintance that wants to join our adventure. All right, so time for questions, if you have.
One. Yeah. What about root case? Yeah, the root case was that developers decided to check configuration each time from the Redis, and you got limits from the AWS. And here is the question. What about architecture review? Because in that case, really the error and mistakes on the developer side. Yeah, that's that's strange. Yeah, to check the really big configuration each time from the Redis and do a lot of stuff, network bandwidth and so on. How you decided to keep it very simple? Because in that case, maybe better to to change the root case, yeah, about this configuration, and not develop a lot of circuit breakers and so on, a lot of other stuff. Yeah. What about that?
Absolutely. So that problem was addressed. I don't remember how did we change the approach, but it was changed, of course. It was done in a different way, but we wanted to prevent Preply of going down for something that we did not expect. So in this case, beyond, let's say, human error that maybe used a tool in the way it was not meant to, we also wanted to prevent depending on the stability of external system. So remember that we had this request queuing. Any request that was taking longer and longer to be responses, it will pile up all the workers that we have in Unicorn. And if you remember, we don't have automatic scaling. We have a cap on the spike. We have limited amount of workers. So we wanted to have some system that could allow us to prevent similar issue, not only for Redis, but for any external component of the system. So this is why we decided to invest time on doing this. Thanks to you for the question.
Hi, have you ever considered adding read-only nodes to your database cluster?
We do, and we have. Yeah, indeed. Yeah, I don't know what to say. So even having read-only nodes sometimes brings issues, right? In the sense that you can have replication latency and so on. But so far we use it. We are promoting them more and more because we want to. You saw the database, the main database, the amount of CPUs that we have. We have been able to scale it down, but still, developers have to be conscious on when to use the replica, read replica in this case, and when to use the main one, to writes, right? If they have any strong reason to keep reads to the master to avoid any the replication lag, that's also okay. But yeah, also, again, I want to remember that we don't have circuit breakers for the database right now. So maybe in the future, when we can iterate more, we can have some safe failover or master to master that we can disable the one that it's, I don't know. We have to iterate on it, or maybe it's just a risk that we assume, and we'll see, right? Yeah, thank you.
And one of the graphics you showed there was a lot of SQL queries, and there was always to select something, no? How you this announcing to developers, this program is using this too much, you need to improve it.
Yeah, but this part, in this example, this is quite normal, let's say. Waffle switches are the feature switches that we use within the company, right? So the whole code is spread with, I don't know how many of them, but maybe thousands of switches to see if a feature, specific feature is enabled or not, in order to send the traffic flow through the code from one way or the other. So it's quite normal that they request this switch status, but normally this is served from cache. In this case, the cache was not there. So all of them went to the database as, I don't know, as when you open the water dump and it brings on everything, right?
Yeah, it looks like.
Yeah.
For that the reason, just sometimes this happen also with us, is like there is a massive query, but there is no cache in the middle, and you need to inform to developers like.
Absolutely.
That is the question. It was, hey guys, you need to check out because this is giving us a lot of problems.
Yeah.
And the other, you are using Elasticsearch, you say?
Yes.
So it's managed by you.
Well, it's Elasticsearch.
Or you are using OpenSearch.
Yes.
Okay.
Yeah, but OpenSearch with Elasticsearch Engine. So we are still on the old
For
engine.
that reason, you sometimes have problems. That was the question, is because it's kind of weird when they're going down also OpenSearch when it's kind of fast.
Mm-hmm.
Because it's managed by Amazon.
Yeah. It's still managed by Amazon, but it's before they started to develop OpenSearch service on OpenSearch. Yes.
The fork.
Exactly.
Thank you.
Yeah, welcome.
Prep to be pro. And without subtitles, huh?